Let's continue our discussion on molecular shapes. Molecular shapes are important aspects of the property of the molecule. As you know, almost all of the molecules are not two-dimensional materials. They are three-dimensional molecules. Therefore, we need to account or understand the shape of a molecule. So as you know, there are linear molecules, there are bent molecules, and we also need to understand from the point of bond angle. This is another property. Of course, also bond lengths between two atoms in the molecule. So the molecular shape is determined by all of the groups that are attached to the central atom, and the central atom also would have either lone pairs or a pair of lone pairs on it. For example, if you just look at a linear molecule on this, if you just say chlorine with its lone pairs, remember to account all of the lone pairs, this is a linear molecule. That means chlorine exists as a linear Cl-Cl bond, as a linear molecule. And there are bent molecules. In bent molecules, for example, let's take water, which is H2O, put oxygen as a central atom because that is the most electronegative atom, and also that's what should be at the center. Hydrogens cannot be at the center of the molecule, as you know. Now, putting the bonding between oxygen and hydrogen, now we have such shape, which is a bent shape. The reason why this molecule would be a bent shape has to do something with the presence of a lone pairs as well. So in any molecule that has a central atom with a lone pair, the shape in most cases would be a bent shape. Now, if you just count electrons around the oxygen, there are only 4, so there are 4 moles remaining as a lone pair. So you have one pair and another pair. Now, if you just look at this, the octet rule is satisfied because there are 8 electrons around oxygen. So the shape of this molecule, if you just account for the image that you are looking at, it is a bent because the presence of the lone pairs and the bond pairs, these are called bond pairs. These are bond pairs, and these are lone pairs. So the lone pairs, usually the shape is determined by the interaction between the lone pair and bond pair. As you know, electrons repel each other. So the whole idea of having an optimum geometry or shape is dictated by the presence of the lone pairs. For example, the lone pair, there is a bond pair, there are electrons, so they want to maximize their distance between them. The closer they are, the repulsion is high. So the shape is determined by how far is the optimum distance. For example, this lone pair and this lone pair should be as far as part possible in the molecule, because the interaction between the two is always a repulsive interaction. So there is a lone pair interaction. This is another lone pair, of course. So the bond angle is determined by the repulsion of lone pairs, bond pair, as well as lone pair, bond pair. All of these interactions are determined what the shape should be look like. That's why it's a bent shape, so that it maximizes the distance between the two groups. The lone pair interaction is very high. It's actually the highest interaction. the bond pair is lower. The lone pair bond pair is low as well. So this is the highest, this is the next low, the lowest we can say, and this is low. This should be between these two. Therefore, now as you see, now this interaction is what determines the shape of the molecule. Now, if you just consider all of the lone pairs and the lone pairs, there are 4 groups that are attached to oxygen. What I meant is, there is one group here, we call it 1. There is another group here. There is another group, and there is another group that's attached to the oxygen. Therefore, actually it has 4 groups that are attached to the central atom, including the lone pair and the bond pairs. Therefore, oxygen actually has a tetrahedral shape. There are 4 groups attached to it. Therefore, we call this a bent, obviously it is bent, and a tetrahedral shape. As I said, this is linear. This is a tetrahedral bent shape, which is dictated by the interaction of the lone pairs and lone pairs, so that they want to maximize their distance between them. Therefore, they push down the bond pair down, so that it would have a bond angle for the tetrahedral in water molecule. The bond angle, which is one of the properties that determines the shape, this is 109.5 degree angle. This is because the lone pairs and lone pairs, they want to maximize their distance between them, so they push down by lone pair bond pair interaction, lone pair bond pair interaction. If you just look at here, the lone pair bond pair interaction would push it down as much as to be 109.5. Here I want also to introduce one molecule. Obviously this is a bent and tetrahedral, so this is not a flat molecule. But I want also to introduce one type of molecule. For example, as an example, borane is a molecule, and it is unique, and there are specific cases why it is unique. Because borane, if you just draw the structure, it is like this. And borane doesn't have lone pair of electrons on it. So, as you see, it has only 6 electrons around it. It violates the octet rule. So, these are some of the exceptions, like borane, which doesn't satisfy the octet rule but exists as a stable compound. So, borane still needs electrons. That's why we'll later on understand why borane is a strong Lewis acid. We'll discuss that in our next chapter. But here, a borane has not a bent shape because it doesn't have lone pair, and it's also flat. And the bond angle between the bond pair and bond pair, this bond pair and this bond pair, the bond, is 120 degrees. This is 120 degrees. This is 120 degrees. So this shape is a planar shape. That means it's flat on the surface. So this we call trigonal planar. If you remember your general chemistry, there are different molecular shapes. This is a trigonal planar shape. There are 3 groups attached to it. That's why we call it trigonal. And it's planar. That means it is just on the surface of the board as you just look at it. So, important points, tetrahedral geometry, you should remember there are 4 groups attached to it, including the lone pairs, 1 pair, 2 groups, 3, 4. And now there is another molecule in terms of linear. For example, if I just want to give you an example, this is an acetylene compound and it's linear. some of the characteristics of this linear molecule. As you see, carbon doesn't have lone pair of electrons, and this carbon also doesn't have lone pair of electrons. So the shape of this molecule is linear, and it is 180 degrees of bond angle. This bond angle is 180 degrees, and as you see, the octet rule is satisfied. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 around each carbon. So this is a stable molecule, but its shape is linear molecule. Here we have discussed tetrahedral, and here we have discussed trigonal planar. As most organic compounds that contain carbon, obviously, have a tetrahedral shape, I will discuss in detail what a tetrahedral shape looks like in discussing what a tetrahedral shape in most organic compounds, especially on carbon, looks like. So by taking the smallest organic compound here would be CH4, which is methane. We call this methane. And if you just drew a loose structure, it would be this. And in a skeletal form would be this. This is what we have studied so far in drawing a loose structure for a molecule. But as you know, as we have already discussed, most of the molecules, they are not flat molecules. They are three-dimensional, especially in carbon, for example. When it is attached to 4 different groups, it has a tetrahedral geometry. So in order to draw a tetrahedral geometry, it means that there are atoms that are on the plane of the board, and there are atoms in and out of the plane of the board. So I remind you to practice this, because most of the organic compounds now would have obviously carbon and hydrogen bonded to them. You need to understand how to draw carefully and precisely what a tetrahedral geometry around carbon is. As I said, here these 4 groups are attached to the central atom carbon. So here is the drawing. You have the central atom carbon, and 2 of the hydrogen, as I said, they are flat on the board. That means they are on the plane of the board. So if you just take hydrogen, it's the bond angle is not 90 degrees like what is depicted here. Therefore, you have to avoid drawing it like this. This was just to show you the loose structure. Now we have gone now to really understand what the shape looks like. So this is about 109 degrees. So the other hydrogen would be here. As I said, these are the 2 bonds that are on the plane of the board. So remember, always in a tetrahedral geometry, especially for carbon, 2 groups, any of those around carbon, are on the plane of the board. Therefore, we just write the straight line shape on the board. But there are 2 hydrogens. One is into the plane of the board, and the other is out the plane of the board. It is sticking out towards me. To show that it is sticking out towards me, I have a wedge drawing of a bolt showing that it is coming out of me. Remember this angle 109 degrees. So now this is 1 hydrogen, and this is coming towards me. It's out of the plane of the board. It is sticking out like this. So it's not on the plane of the board. The next one is to show that this hydrogen actually is going into the plane of the board, so it's not right on the plane of the board, but inside to the plane of the board. So as you see now, you have a three-dimensional molecule, this is a tetrahedral shape. So this can be for any one of those. For example, I can still draw this. I can make this in and out. For example, this could be out coming to us, towards me, and here this hydrogen going into the plane of the board, and I can just draw another hydrogen and another hydrogen on the plane of the board. So these are equivalent. I'm just rotating everything. If you just flip it that way, that's what you see. So you have to be careful in drawing a tetrahedral shape, because that is the one which is mostly present in organic compounds. So this is for a simple molecule CH4 methane, but how about if you had CH3 CH3? Okay, now you can draw this. That means if it is this is a, let's say the skeletal form of the drawing, it would look like this. But as I said, they are not on the plane of the board. So how do I draw this? So it's kind of what you have to do is one of the hydrogens, it can be any one of the hydrogens, is actually replaced by now CH3. So if you have 1, 2, 3 hydrogens, if you have 1, 2, 3 hydrogens, this hydrogen actually has been replaced by another carbon. That's how the chain continues. For example, so if it is this carbon, let me just mark it like this. If that is a carbon, around it there are this hydrogen, which is this hydrogen, and if you just have another hydrogen which is sticking out to me with the wedge form, and another hydrogen going in. But instead of this hydrogen, now I have this whole unit, this whole substituent is around here. So that means it is, if I have one in, one out, one on the plane of the board, the next substituent should be also on the plane of the board. That is this carbon right here. So this is the carbon that we have here. And now still this carbon is a tetrahedral shape. What I will do would be, then if I have one of the hydrogens on the plane of the board, I will just draw it like this. Now the rest of the two hydrogens, one would be in, one would be out. For example, it could be hydrogen out, hydrogen into the plane of the board. So you have CH3, CH3 in a tetrahedral shape. So if I have to continue again, for example, in another molecule, let's say CH3, CH2, because you cannot do CH3 if there is a substituent on this. So if I have CH3 again, what I will do is I will replace one of the hydrogens with a carbon and continue the sequence. So this is CH3, then one of the hydrogen would become a carbon substituent, so this would remain as a CH2. So you should be very familiar in drawing a structure of organic compounds with a tetrahedral bonding. So usually students get confused in terms of drawing a tetrahedral carbon. I encourage you to practice this and draw as many chains as possible with a tetrahedral geometry in carbon, around carbon. So you can continue the sequence CH3, CH2, CH2, CH3, more than 4 carbons, 5 carbons, 6 carbons. you'd also see a sequence which looks like actually this. So after a while, you'll be representing not anymore of with all of the hydrogens, but something like this. This is suggesting that there are one hydrogen in, another hydrogen coming out. Here there are 3 hydrogens. That means 2 of them, one is out, one is in, the other is on the plane of the board. See how easy would it become when once you know what the sequence looks like. The sequence looks like up, down, up, down. These are carbons. Remember, these are carbons. These are carbons. So you should be familiar with drawing such structure for organic compounds. For example, here the hydrogen is sticking out, another hydrogen going in, but the 2 carbons are on the plane of the board. You remember, 2 of the substituents on carbon should be on the plane of the board. So we made the skeleton, the sticks on the surface of the board, and the hydrogens coming in, coming down. Here, for example, you have hydrogen in and hydrogen out. This is still tetrahedral. Look the shape. You have this substituent and that substituent are on the plane of the board, while the 2 hydrogens are in and out and in. I will also continue this. You can also draw this. One hydrogen is sticking out to the surface and into the plane of the board, and it continues. You have hydrogen out, hydrogen in, and 1 hydrogen on the surface of the board. This is how the chain continues. So it's very easy once you adapt or practice for a single carbon, a tetrahedral geometry. Remember, the angle is close to 109 degrees because it is a tetrahedral shape. And keeping that, you need to practice for a tetrahedral shape because most of the organic compounds contain a tetrahedral carbon. And we'll also see a linear carbon where the shape is a linear one, and so on. So I will continue with more of a drawing of organic structures. Now we'll see also drawing some organic structure, since this is a review of fundamental organic chemistry or organic chemistry introduction. There are what we call condensed structure. If you, for example, have this, where there is a carbon-carbon bond, each one of this shows you this one is a condensed structure. So this is, if we put it in a formula, this would be C4H10, I believe. That's a formula. This is a condensed structure for C4H10. What does it look like in skeletal structure? In a skeletal structure, what we call is this. So the skeletal structure obviously doesn't show the 3-dimensional nature of this compound, as well as it doesn't show the real bond angle. So what I would add to this, or the most practice that we do in organic chemistry, would be you have a condensed structure, we use that. Sometimes the skeletal structure could be used, and in a more refined way, this structure also can be drawn as, like what I have discussed before, a structure where it shows the 3-dimensional nature of this skeletal structure. So if I have carbon as the center, for example, here, and if the hydrogens are displayed as out to out of the board into the board, and one of the hydrogens would be on the plane of the board. The next hydrogen, instead of hydrogen, what I have as a substituent for this to be octet is another carbon. Therefore, that carbon should be on the plane of the board, because you see this, if you just consider these two hydrogen as a substituent on this carbon, the third one is this, the fourth one would be this carbon. Therefore, I put it on the plane of the board as carbon. So this is this carbon right there. How many hydrogens do we have? 2 hydrogens, and the rest would be a substituent. So the 2 hydrogens can be displayed now. So what I decided to make is all the carbons to be on the plane of the board. That's why this carbon, I would say this carbon is on the plane of the board, the next carbon is on the plane of the board. But the hydrogens are in and out. For example, I can just make out of the board, into the board. Now, next one should be the carbon, that is the fourth item that's substituted to this. Therefore, I will put it on the plane of the board. So this third carbon, which is this one, is on the plane of the board, and it has 2 carbons on it, 2 hydrogens, sorry. So the other carbon is the next carbon, which is down here. So remember to draw the hydrogens. One into the plane of the board, the other is out into the plane of the board. Remember the bond angle, the bond angles should be 109. So the next carbon, which is this carbon, is on the plane of the board. So now I have 2 of the hydrogens would be on the, at least one of the hydrogens should be in the plane of the board, because there is one already on the plane of the board on this carbon. So this hydrogen, let's say, is on the plane of the board. And the 2 hydrogens, the 3 hydrogens now remaining would be, actually there are 2, into the board and out of the board. See how it looks like? This is how this molecule is redrawn in a very usual and most organic chemists, they use this one. Actually, if you see all organic structures in your textbook in the future, you would see that this is actually equivalent to saying that by removing the hydrogens, meaning we know that they are there, you start with this carbon right there, down, up, down. There are 4 carbons, 1, 2, 3, 4 carbons. The rest are hydrogen. So this structure is actually this: 1, 2, 3, 4. Remember, there are 3 hydrogens on this, there are 2 hydrogens on this, there are 2 hydrogens on this, and there are 3 hydrogens on this. So with condensed structure like that, you have to write all the hydrogens, carbon, and all that. But once you become very familiar with how to draw the organic compounds in a tetrahedral form, you go to the next step and start practicing to draw this tetrahedral shape, which is actually how the molecule exists. So for a sake of simplicity, and in the future when you become more practitioners of organic chemistry, we just write 4 carbon like this: 1, 2, 3, 4 carbon. They're the same, starting down, and 4 carbons, they're all the same. So now in writing the organic structure, now you have a condensed form, a skeletal form, and actually a tetrahedral form where you have all of the hydrogens. And now here are actually the most mostly used in the future as well. That's what we will be using. So practice in drawing such structures. Organic compounds are not always chains. They are also cyclical. There are cyclic compounds that are also organic compounds. So in the next section, I will show you some cyclical structures of organic compounds with some also examples of condensed and skeletal structures. Continuing our discussion on structures and tetrahedral structures with skeletal and condensed structures, one thing you should remember, organic compounds also can exist as a cyclic form of different sizes. Here, if you see 3 carbons that are C3H6 in a skeletal form, as you see it, and each carbon is depicted as a tetrahedral center where you have the main frame on the plane of the board, and the hydrogens are, one is towards me out and the other is into the plane of the board. All of the hydrogens, as you see, are displayed as in and out of the plane of the board, while the main skeletal form of the cyclopropane, the carbons, this is each are carbon here, one carbon, another carbon, another carbon. So this is a C3H6, a tetrahedral, single bonded cyclopropane. We call it cyclopropane, propane, because there are 3 of them, 3 carbons in them, and it's a cyclic structure. Here you see a structure with 4 carbons. It looks like a square, but the hydrogens, if we were to draw, this is a condensed form right now, as you see it. But with the skeletal form, if you include the hydrogens, for example, one hydrogen out of the plane of the board, because the 2 skeletal form of the cyclobutane are on the plane of the board. It's as if you just show it as a flat on the plane of the board, this and this are on the plane of the board. So the hydrogens definitely will be in and out of the plane of the board. As I said, 2 groups in a tetrahedral geometry has to be on the plane of the board. Here as well, if I have one hydrogen coming out, the other hydrogen should be going into the plane of the board. Similarly the same, one hydrogen out of the board and the other one into the plane of the board. Exactly the same, hydrogen out and another hydrogen into the plane of the board. Similarly, you can draw for cyclopentane, where you have 5 carbons and 10 hydrogens. If you just count, each carbon has to have 2, obviously, because you cannot have more than 2, and therefore the C5 would be C5H10. It's called cyclopentane. That's 5 carbons. And the drawing, you can complete this drawing by having hydrogen in, hydrogen out. Exactly here the same, hydrogen out of the plane of the board and into the plane of the board. So you should always keep the carbon to have a tetrahedral configuration in organic compounds when they are making single bond. So as I continue my discussion, similarly there is a cyclohexane, a more common compound as well. So you have hydrogen out of the plane of the board, into the plane of the board, hydrogen out of the plane of the board, into the plane of the board. So you should be very familiar by drawing these skeletal structures where you have the hydrogens in and out to show that it's 3-dimensional shape of the molecule as well. So this shows you all how tetrahedral geometry can be drawn in organic compounds. So this, as you see, this structures, can be carry also a charge. That means one of the hydrogens can be removed, or you can have no substituents. At that time, you would have a charged species. For example, if I take a cyclohexane, and you have obviously each one of has in the future this is equivalent to saying the same. So we may not show all of the hydrogens, but just keep it like this. So we know that this is C6H12. So we can denote in a very condensed way this compound. In future practice in organic chemistry, you should be familiar with just drawing like that to represent this, which is a C6H12. So if I just show on this carbon, for example, if I show this, a charge, that means one of the hydrogens have been removed or it's not there. But instead of that, lone pair of electrons are kept on that carbon. So if you just see the octet rule, you have 2, 4, 6, 8. So this has only one hydrogen. It means that instead of that carbon carrying 2 hydrogens, the bond has been broken and you have a charge on it. Similarly, if the hydrogen takes all of the electrons with it, without just leaving it, you have only one hydrogen and a plus. That means there is one hydrogen on this carbon, but the pair of electrons are gone with the hydrogen. So this shows you just one hydrogen on this with a pair of electrons. If you calculate formal charge on that carbon, that's what you will see, and you can calculate a formal charge on this. How do we do the formal charge for this one, for example? The formal charge is a -1, a formal charge is a +1 for that carbon. The reason being, carbon has a valence electron, so 4 minus, there is no lone pair on this. There is, actually it's not on, you have 4 valence electrons, 4 minus 0, and half of the bonding electrons. That means 1, 2, that means 2 electrons, 4, and remember there is one hydrogen on this. Even though the other one has left, there is one hydrogen. So there are 6 bonding electrons. That means half of 6 would be 3. 4 minus 3 is a +1. In this case, you have valence electrons for that carbon is 4 in the formula. 4 minus 2, that's the lone pairs, that is 2, and half of the bonding electrons, 3, that is 4 minus 5, which equals -1. So practice this so that you know why the charges are a minus and a plus. So by just calculating the formal charge, you know why we have a minus and a plus for a charged species. These are called charged species, charged molecules. So the charge is created either because the hydrogen has left 2 of its bonded electrons and left as a proton, or here the hydrogen left as a hydride with a pair of electrons. So you can see these are differently charged molecules. And I want to encourage you to practice these cyclic forms of organic compounds as well. In our next session, we'll be discussing a very important concept called hybridization. Right now, we'll be discussing hybridization. This is a concept where the orbitals that are involved in making a bond are optimized. That means the energy level of those valence electrons, where they are in the valence shell, would have an appropriate orbital so that they make a perfect bonding between two atoms. Remember that when we say orbitals, each atom would have, for example, if we consider hydrogen, it is a 1s1. If we consider carbon, it is 1s2, 2s2, 2p2. So if you just look at here, the S is paired to P has 2 electrons. That means if you just expand this in the px orbital, there is 1. In the py direction, there is 1 orbital. So the unpaired number of electrons, if you just look at here on carbon, they can only take maybe 1s of this, 1 electron, to pair up each. So the maximum number of hydrogens that a carbon can take based on this orbital distribution, so this is the number of electrons in the orbital, is, for example, if you just bring one electron, one of the s, interacting with this, it makes 1, another 1, so it would make CH2, not CH4. The compound that we know as a stable organic compound is methane, which is CH4, not CH2. So how do we make CH4? Based on the electronic configuration of hydrogen and the electronic configuration of carbon as they are. So it is not possible to justify how CH4 is formed just by looking at the orbitals. So hybridization is a concept where you are justifying or you are mathematically expressing how the orbital overlap happens, and the bond actually is made and it is stable to form a tetrahedral methane compound. So hybridization is that is the concept. It's not just the orbitals that are found in each atom that just without any hybridization they would make the bonding. So CH2 doesn't exist, CH4 exists. So how do we accommodate 4 electrons or 4 of the hydrogen's orbitals that can come here? Because the valence electrons on carbon are, let's say, on the p, these are paired already, so you cannot bring anything according to what we have. So if you have 2px1 and 2py1 for the 2p2 configuration, the maximum you can have is 2 hydrogens, but CH2 doesn't really exist. So this concept or this idea of having CH4 can be only justified by hybridized orbitals. What are hybrid orbitals? So let's review now. So when we say orbitals, these are the lobes that contain the electrons to make the bond. For example, if you have hydrogen gas, which is a linear molecule, a non-polar covalent bond between the two is made from 1 electron of 1s1 and another 1s1. They overlap and make the bond to make this covalent bond by sharing these 2 electrons. So they make a sigma bond because this is made from 1 s electron. S orbital is a circular one, a sphere type. This is the 1s orbital where one of the electrons exists, and another one is 1s for this. So there are 2s orbitals. When they combine, they become a cylindrical shape with the nuclei like this. And this is original one of the hydrogens. So you have this. So the bond that is made from SS overlap, the orbital that's made from SS overlap is called sigma bond. A sigma bond. Sigma bond is a single bond. So now we are going into details of what this bonding looks like by way of hybridization. So this is a simple case where an S and S overlap. So they make this cylindrical shape molecule where this bonding, where the electron density is high here, is a sigma bond, denoted by this symbol as sigma bond. Sigma bond is very strong, and also it is the longest one. We'll consider that later on. So sigma bond is what exists between two hydrogens. It is made from the overlap of one s orbital and another s orbital. So that made a sigma bond. Next, we will see a tetrahedral shape that is making a methane compound out of 4 hydrogens and 1 carbon. That is made by hybridized orbitals, not by just the combination of the atomic orbitals. These are atomic orbitals. Atomic orbitals. Just as these are atomic orbitals as well. But in order to make organic compounds, there is a concept what we call hybridization, where the atomic orbitals make certain transition and make appropriate energy level orbitals that can also perfectly overlap so that they can make a bond. So in the next discussion, I will show you how a tetrahedral bond in methane is made from hybrid orbitals. So CH4 is made not from atomic orbitals, but it is made of hybrid orbitals. That's the concept of hybridization. So those are hybrid orbitals. How are hybrid orbitals made? That is in the next discussion, what hybrid orbitals are. We told you about hybrid orbitals. We'll now discuss how methane, which is CH4, how methane is made. First, let's see just the atomic orbitals by themselves. For example, carbon in a ground state, that means unexcited carbon, which is a 1s2, 2s2, 2p2 configuration, would have its orbitals arranged by energy diagram. For example, the lowest is 1s energy. If you remember in your general chemistry, there are 2 electrons in the 1s. In the next 2s, there are 2 electrons with the spins, they are up and down. And there are, in the 2p, there are 2 electrons. If you remember, 2p orbital is a px, a py, a pz. There are 3 of them, if you remember, px, py, pz. But s is just spherical in shape. But in the p orbital, if I just show you the shape, one is in the py direction, right? One is in the px direction, one is in the pz direction. These are the 3 orbitals that each one of them would contain 2 electrons, 2 electrons, 2 electrons, a maximum of 6. But in carbon we have 2. Therefore, I would just make 2 electrons in this spin. So now this is just a ground state configuration, just the atomic orbitals for carbon. So as I already told you, if you just bring 2 hydrogens from an s orbital, you can only make paired up. Always bonding is pairing up. So this can only take 2 hydrogens. Therefore, this configuration cannot allow you to make CH4. So what do we have? Now, from this, what we are going to do would be to hybridize these orbitals. That means if you hybridize, that means if we make a hybrid of an s and a p, if you take one of the s and hybridize it with the 3 of the p orbitals, you would make sp3 hybrid orbitals. So what does it mean is you have s and p, which are energetically very close, so you cannot hybridize this with that, but hybrid is to say that you are just trying to mix them. So the hybrid orbitals look like, out of this, hybrid orbitals. So what I did is just to mix up all of this, so the electrons have now space to go everywhere in the p. So this one electron would jump to this. So what it looks like would be a hybrid orbital where one of the s and 3 of the p's are hybridized. You already know you have these electrons, and there is one electron that jumped to this, one electron. There is one electron which was already here and occupies this. Look at this now. Now, this is a hybrid of an s and 3 of the p. That's why it's called sp3 hybrid orbital. Energetically, they are all the same. They are equivalent. And also, they contain a single electron in each orbital. So sp3-1, sp3-2, sp3, sp3. So now, what we have done, to just review back again so that you will not forget, this is a ground state configuration. Let's say this is ground state configuration. The ground state configuration doesn't allow you to make CH4. It's because the only thing you can pair up is a maximum of 2 hydrogens with 1 electron coming from each one hydrogen. Therefore, you can only make CH2. But CH2 doesn't exist in nature. CH4 exists. Therefore, our mathematical approach why CH4 is formed is one of the s orbital is mixed with 3 of the p orbitals to make 4 sp3 orbitals, meaning s and 3 of them, sp3 orbitals with single electron distributed on all over the orbitals. Now, since you have one s1 in hydrogen, right? Hydrogen has 1 electron in its valence shell. Now, if you just bring 1 hydrogen here, you are pairing up. The sp3 is making a bond with one of the s to make a paired electron, and another hydrogen with one s making another pair, another hydrogen, one s1, making a pair here, another hydrogen making a pair here. So now what we have is 4 sp3 orbitals that have bonded, because this is an s, that have bonded with sp3 to make a molecule CH4 through sp3 hybridization. Now we can justify how CH4 is formed. In nature, you have methane, not CH2. Therefore, the way the orbitals have made possible by expanding or by mixing these two orbitals, the s and the p, we made an equivalent. They are all equivalent now. Equivalent orbitals, and they are also called degenerate. Degenerate means of equal energy. Equal energy. So now, since they are all equal energies, they have equal probability for making or accepting 4 electrons from hydrogen of 1s orbital. So I will show you the shape, and also if you remember, how was this tetrahedral shape formed? It all depends on the hybridization and the angle that I showed you, about 109 degrees for sp3 orbitals, came from this calculation. So in the next discussion, I will just show you what sp3 hybrid orbitals look like and what is the shape that made CH4 in a tetrahedral geometry. Now we have the sp3 hybrid orbitals that are equivalent. As I already indicated, for sp3 hybrid orbitals, they contain 1 electron each in carbon. Carbon with sp3 hybridized orbital looks like this. 4 of them are identical in energy, and each one of them contain 1 electron. So there are 4 of them. They are made of 1s and 3 of the p orbitals. That's why they are called sp3 hybrid orbitals. They are made of 1s and 3 of the p orbitals in carbon to generate degenerate orbitals or equivalent orbital orbitals that contain 4 electrons. So how does they look like? If you remember, CH4, for example, looks like this. When I was discussing about tetrahedral shape, this was my discussion earlier. So the sp3 orbitals are actually the ones which are shown here, basically. So let me draw the sp3 hybrid orbitals. So they are made of 1s and 3 of the p, and their shape looks like this. The lobes are like this, one of the sp3, another sp3, another sp3, and another sp3. There are 4 of them. Each one of them have 1 electron, 1 electron, 1 electron, 1 electron. So this is basically what you see in sp3 hybrid orbitals. Remember that since they are made of s and p, the p has a shape that's like this. So the hybrid orbitals have actually a lobe, which I didn't show because I don't want to complicate. This is actually the sp3 orbital. This is how it looks like, but I didn't show this small lobe here in all of them. But that's how the sp3 hybrid orbital looks like. Now, if we were to make the compound, this is just a carbon with its hybrid orbitals. We can bring now the 1s of the hydrogen with 1 electron. So it is spherical in shape. The s orbital is spherical. So it can come like this with 1 electron paired up. This is hydrogen of 1s. If you just bring it to make the bond between these two, there is 1 electron there, and this is a 1s of the hydrogen. This is also hydrogen here, 1s, to make a pair, and here also 1s of the hydrogen to make this pair. This is actually what this molecule looks like when you saw it in hybrid orbitals. So this is 1H, this is 1H, this is 1H. So a methane is actually made from 4 sp3 orbitals that are overlapping or make bond with 1s of the hydrogen. So 4 of the sp3 hybrid orbitals, sp3 hybrid orbitals, 3 means 3 of the p, and 1 of the s, with a total of 4 electrons on them, overlapping with a sigma of 1s are actually what is making the bond, the 4 bonds. And as I already told you, in order to improve the repulsion between bond pair, the tetrahedral geometry is a preferable one for sp3 hybrid orbitals, so that they can look like the distance between them is 109 degrees. 109 degrees, the angle. The angle is 109. So that is how a hybrid orbitals are making a CH4 molecule. So it's just more complicated than like what you see here in a tetrahedral stick form, like I showed you earlier. But it's made from hybrid orbitals, and now you know how the 4 orbitals, the sp3, came from hybridization of 1 of the s and 3 of the p orbitals in carbon. So carbon comes with this 4 sp3 hybridized orbitals. So these are all hybrid orbitals or hybridized orbitals. And now one important point I want to mention, the overlap of sp3 with a hydrogen with 1s always form sigma bond. So that is a sigma bond. It's not a double bond, it is a single bond. It's called sigma. A sigma bond. So the overlap of an sp3 with 1 hydrogen when it comes in to make a bond, that is a sigma bond. So remember, this is a sigma bond, this is a sigma bond, this is a sigma bond, this is a sigma bond. They are made from the overlap of 1 sp3 with 1s to make this bond. So this is overlap of sp3 with 1s, that is a sigma bond. So a sigma bond is made either by, like in hydrogen molecule, an overlap of an s orbital with another s orbital make a sigma bond. Another sigma bond is an overlap of 1s with a hybridized sp3 is always a sigma bond, always. So don't make any mistake in assigning what kind of bond it is. If it is sp3 and if it is overlapping with an s orbital, for that matter with any other orbital, it can only form a sigma bond. Now we are also, together with hybridization, we are also learning what type of bonding it is. It is a sigma bond. It's called a sigma bond. Okay, in the next discussion, we will be looking at sp2 hybridized orbitals. The sp2 hybridized orbitals are made with 1 of the s orbitals of carbon and with another 2 of the p orbitals in p orbital in carbon. So there is sp3, which we just discussed, from hybridization of 1 of the s with 3 of the p. There is another one which is called sp2. There is also another called sp. So these are the type of hybridizations. These are type of hybridizations that are possible. sp3, sp2, sp. So since we have just finished the discussion on sp3, I will pass on in the next section to sp2 hybridization. Discussion continues. Now I want to show you what sp2 hybridized carbon looks like in the orbital formation and how the bonding happens. So in ground state carbon, you have a 1s2, 2s2, 2p2 in electronic configuration. So these are just atomic orbitals. When you say it's hybridized, that means in excited states of this, we are trying to make sp2, meaning 1s and the 2p orbitals are mixed. That means you are creating, usually we don't consider the inner one, that's the most close to the nucleus, but we are just considering valence electrons. So we are mixing one of these orbitals with two of these p orbitals. That means we are just taking one to make three sp2 orbitals. These are sp2 orbitals of their lower energy, but one of the orbitals, because there are 4 atomic orbitals, 1, 2, 3, 4, but one of them is not hybridized. So it will be a little high in energy. So it remains, it could be the px, the py, or the pz. It doesn't matter which one, but one of the p orbitals is not mixed because we are just mixing one of the s and two of the p, which are degenerate orbitals. Remember, I have said all hybrid orbitals or hybridized orbitals have of the same energy. That's why we call them degenerate orbitals or equal energy. One of them is a p orbital with 1 electron, which is not hybridized, but the 4 electrons are distributed like this. So 1, 2, 3, 4 electrons. So this p orbital, one of the p orbital, is not hybridized. So this is not hybridized. That's why it's at higher energy than the 3 ones. These are hybrid orbitals. So this is how sp2 hybridization happens from a ground state of carbon, for example. It could be oxygen. You can do the same hybridization pattern, but here carbon undergoes sp2 hybridization like we have seen in sp3. So there are now 3 sp2s and 1 p orbital. So if we were to draw this in a drawing form, the sp2 orbital configuration would be sp2, one of the sp2s with 1 electron, another sp2 with 1 electron, this one, and another one sp2 with 1 electron on this. But remember that, as I said, this sp2 are now hybrid orbitals. These are the ones which will be, for example, making a bond. But remember, there is a p orbital still on carbon. That p orbital is perpendicular to the sp2 orbital. The sp2 orbitals are aligned with 120 degrees. Remember now, for sp3, we said it is 109. For sp2 configuration, since there are 3 lobes, they are in space at 120 degrees. Remember that. Now, if we consider all of the sp2s are on the plane of the board, there would be the p orbital perpendicular to the plane of the board. What it means is it's 90 degrees to the sp2. For example, if this is all of the sp2 orbitals with carbon at the center and a flat molecule, a flat configuration, then the unhybridized p orbital stands at 90 degrees to this. So I will be just drawing it so that you'll identify it as a p orbital, but it is 90 degrees to the surface of this sp2 orbitals. So this is 90 degrees to the red color is unhybridized p orbital with one electron. So it's only one electron on a p orbital. So that's the p orbital. So in chemical bonding or in making a bond, what happens is, for example, to give you an example where we have a pi bond, so a bond that's made through a pp interaction is called a pi bond. But let me give you an example. Just keep this in mind. We have C, H, 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 H. This molecule is called ethylene. We'll discuss it later in detail in the future. It is ethene. It has a double bond, one sigma bond and one pi bond. I will explain which one is a pi bond. So suppose this carbon is an sp2 hybridized carbon. Actually it is sp2 hybridized carbon, exactly like this. If I make another one exactly like this, C, sp2 hybrid orbital, sp2 hybrid orbital, and still one p orbital remains unhybridized on this carbon as well, exactly like p. It's exactly 90 degrees to the surface. So this, all the sp2s are on the plane, and then the p orbital is 90 degrees to the plane of the sp2 hybridized orbitals. Therefore now, if you just look at this, this actually is made by the overlap of this sp2. So this sigma bond is the overlap of this. So they come, make the bond. This is a sigma bond. Sigma bond. This is the sigma bond right here. And the other one, we call this a pi bond. This bond is a pi bond. That is made by the ones which are sticking like this, the p orbitals, which are not unhybridized, but each one of them have one electron on them. They make a bond. So that is the pi bond from this carbon to that carbon. It's called a pi bond. A pi bond is made from unhybridized p orbital interacted with another p orbital, unhybridized. Okay? Now, after having all this, remember, hydrogen has an s orbital which can easily overlap with sp2 as a sigma. This is one s with one electron, that's hydrogen. This is one s of hydrogen with one electron, with one s of hydrogen with one s of hydrogen. This is basically how it looks like a hybrid orbital that is making ethylene or ethene compound. So now let's identify again each one of them as a review. This pi bond, the top one, to make a double bond, the double bond is made of one sigma and one pi bond, a double bond. The pi bond is made from the interaction of unhybridized p orbital on this carbon and p orbital on the other one. So that makes a pi bond. But the sigma bond between this carbon to that carbon is made through a sigma type interaction, sp2, sp2. Always remember, hybrid orbitals, they always make only sigma bonds. Unhybridized p orbitals always make pi bond. So pi bond is the interaction between two p orbitals, a pi bond. A sigma bond is always made of the interaction between two hybrid orbitals or unhybridized 1s orbital of hydrogen with any hybrid orbitals like sp2. So this is an ethane molecule where you have a sigma bond. How many sigma bonds? We have 1, 2, 3, 4, 5 sigma bonds. Ethene is formed from 5 sigmas and 1 pi bond. So I want you to review this at home. An ethene or alkene is made of 1 pi bond from the interaction between pp on each carbon, that makes a pi bond, and 5 sigma bonds. Sigma is this bond, sigma, all of these are sigma, 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 and this one is also sigma. There are 5 sigma bonds and 1 pi bond. I want you to review this. In the next section, I'll show you an sp hybridization and demonstrate with an organic compound to show you how an sp hybrid orbitals are combined to make a compound, a stable compound. And the geometry, as I said, sp2 is 120 degrees. This is important for you to remember. The sp2 has a 120 degrees orientation because of the best overlap for the sp3s. But the p bond or the pi bond, the p orbital is perpendicular to the surface of the sp2 hybrid orbitals. So if you just look at this, if this is a molecule containing the carbon, like flat like this, the pi orbitals are made from this overlap, from standing out, the p orbital standing up like this, making that interaction. That is a pi bond in sp2. So in sp3 hybridization, there is no pi bond. In sp2 hybridization, since there is one left unhybridized p orbital, the unhybridized p orbital makes a pi bond. So I will proceed to the next section, which discusses sp hybrid orbitals. Okay, now we'll be discussing sp hybridization. The same format, the electronic configuration of carbon before hybridization is 1s2, 2s2, 2p2. But now when we say sp hybridization, we meant that one of the s orbital is hybridized with one of the p orbitals. That means 2 p unhybridized orbitals would remain without being hybridized. So let's do the hybridization. The hybridization would give you 2 degenerate orbitals of sp hybridized. That means one of the s and one of the p would hybridize, and they will contain 1 electron each. But remember, unhybridized orbitals, which are the remaining p orbitals, are 2 of the p orbitals are at higher energy level than the hybrid orbitals. The hybrid orbitals are lower in energy, but still the p unhybridized orbitals, orbitals remain at high energy. Now, if we were to draw this on a carbon, the actual shape looks like you have two of the sp orbitals. So as I said, the bonding pair, usually where the hybrid orbitals are, usually they want to configure as far apart as possible. Therefore, if you have two groups, you only attach them in a 100-degree orientation, as far apart as possible, with one electron here, one electron on this. So this is the two sp hybrid orbitals. There are two sp hybrid orbitals, and they will be configured as this, so that the bond angle between the two would be as far as possible, which is 180 degrees, which is always known for sp hybrid orbitals. So if I had another carbon, for example, to make a bond, this would have also another sp with one electron, then they are making a bond, and here there is another sp with one pair. Now let's satisfy this by making a bonding with hydrogen, for example. Hydrogen has one s with one electron to make a bonding situation like this. That is a sigma bond. Remember, always a hybrid orbital with any orbital makes an overlap, which is a sigma type bonding. Here also, if we were to bring on one hydrogen, we have one s with one electron that is being shared to make a bond. So this is how the sp configuration looks like. But remember, you have two anhybrid orbitals in each one of them. So let's say if you have this is the sp orbital of which is containing carbon, there are p orbitals on both, and there is another p orbital in the z direction. So I will just draw the remaining p orbitals, the unhybridized p orbitals on this. So one of them is 90 degrees to the other. So you will have this p orbital containing one electron, and the other p orbital similarly would have, they are equal size, but I'll just draw it here with one electron. So this is, each one of them have, so they would have four of them. So now the other p orbital is 90 degrees to the other one. Therefore, I will just draw this. So it's 90 degrees to this p orbital with one electron here, and this is a p orbital. This is the same p orbital. So this p orbital and that p orbital are 90 degrees to one another. So this one also has a p orbital. So they look like this. So this two p orbitals are the unhybridized p orbitals. Now remember, all hybrid orbitals make a sigma bond. So this is a sigma bond. Here we have hydrogen, which is already made a bond. This is hydrogen, obviously. Now when you make a bond, the unhybridized p orbitals make always a pi bond. So this and that would pair up their electrons, they make a pi bond. This is a sigma bond. This is a pi bond. Still now, furthermore, the other 90 degree oriented p orbitals also make a pi bond, because it's a p overlap. So this actually, when it's representing a molecule like this, so it's acetylene with sp hybridization. So it looks like this. So if we were to account, we have 2 pi bonds, right? 2 pi bonds, because this pp interaction gives you 1 pi bond. This p interacted with another p gives you the second pi bond, and the sigma bond, which is the hybrid sigma bond here, hybrid sigma bond, and this is another sigma bond, this is another sigma bond. So this molecule, the acetylene, would have 3 sigma bonds and 2 pi bonds. So this is how sp hybrid orbitals makes up of a triple bond. So sp2 makes a pi bond, which is a double bond. sp also make a 2 pi bonds and 1 sigma bond to make a triple bond. So now sp3 always makes all sigma bonds. sp2 makes 1 pi bond and 1 sigma bond, that means a double bond. sp hybridized orbitals can make 2 pi bonds and 1 sigma bond, that is a triple bond. Now, so far we have studied a single bond, a double bond, and a triple bond, and they are made through hybrid orbitals. Next we see properties of some of the triple bonds, this double bond, and also a single bond in terms of bond length and bond angle. In terms of examples of those molecules we have seen so far in terms of sigma bond, for example, if you just have carbon, these are all sigma bonds. As you see, they are single bonds. They are made through sp3 hybrid orbitals. These are all sigma bonds here. So this is an example for an sp3. This is called ethane. All are sp3, and they are all sigma bonds. As you see, there is no double bond. Here, for example, ethane with 1 double bond and 1 single bond across. This has 1 sigma and 1 pi here. Exactly, those are double bond, and it's called ethene and alkene. And the hybridization for this carbon is sp2. This carbon is sp2. So this is an example for sp2 hybridization. And if you further see the compound we already just discussed has an sp hybridization, and it has between the carbon-carbon bond there are 2 pi bonds and 1 sigma bond. The hybridization is sp between the 2 carbons. So this is just a summary of hybrid orbitals when you see them in a molecule. So here, the carbon-carbon bond, one of the properties of a sigma bond, it is rotatable. They can rotate. They are not free. They are not rigid. The carbon-carbon bond can rotate. So there is rotation across the carbon-carbon bond. The carbon-carbon bond can just rotate. If you just hold this one, this can rotate. So the rotation is possible. Here the carbon-carbon double bond, unless you break it, doesn't rotate. Does not rotate. Obviously, the triple bond will never rotate across the carbon-carbon bond. The CC bond does not rotate. Here the CC bond as well does not rotate. So these are some of the properties. For example, rotation is possible across the single bond, across the sigma bond. That is sigma, just one sigma. You can rotate the sigma bond. If you just consider the bond length in picometers, for example, this is 153 picometer, and the carbon-carbon bond is the carbon-carbon as you actually the carbon-carbon triple bond is only 121 picometers. That means, as I probably mentioned earlier in our earlier lectures, the carbon-carbon triple bond is the shortest. So the longest would be the carbon-carbon single bond. The carbon-carbon single bond is that much picometer, and the carbon-carbon triple bond is that much picometer. So as you see, the carbon-hydrogen length also is the same. For example, here it's longer, here it is shorter, even the carbon-hydrogen bond. Carbon-hydrogen bond is much longer than the carbon-hydrogen that's attached to a triple bond. So these are some of the properties. So if you just consider the S character of this, basically, if you have an sp carbon here, which is sp hybridized, it has 50% S character and 50% P character in the hybridization. And if you just take sp2, sp2 has 33% S character and 66% P character, a total of 100. But if you take sp character for this is 25% and P character is 75%. This is just a ratio, because if you take sp3 and if you add up all of them to 4, so S is just one part of that, so it is 25%. So those are the different characters you need to remember. And also, when I say S character, whenever you have S character, more S character means it's more electronegative, or it can accommodate or can carry negative charge. That's what it means. But if you have more P character, it's more electropositive. So for example, if I consider this carbon with much more S character than this carbon, if somebody asks you which one is more electronegative in nature, so the carbon on sp, since it has more S character with 50% S character, this carbon is more electronegative than this carbon. And if you compare this carbon with 33% S character on this, is more electronegative than the one carbon on alkane. So overall, if you just look at this, which one is more electronegative atom in this would be the one on sp hybridization. So orbital that has 50% S character is more electronegative than an orbital which has only 25% S character, which would be less electronegative. So those are some of the properties you need to remember when you are thinking of hybridization. So first you have to understand what kind of hybridization that atom has. Second, you should always remember the bond lengths between two hybrid orbitals, for example, a triple bond between two carbons, is a much shorter bond length than a carbon-carbon single bond. In terms of strengths as well, probably I have mentioned it in some of the sessions, carbon-carbon bond, a single bond, much weaker than a carbon-carbon double bond. A carbon-carbon double bond is weaker than a carbon-carbon triple bond. This is the strongest bond between the two carbons. So carbon-carbon triple bond has the strongest bond strengths. And next we'll see some of electronegativities and also some of dipole moments in a molecule. Now we'll review some of the properties of polarity of some compounds and also electronegativity difference or based on electronegativity scale. As you know, when we go from left to right in the periodic table, electronegativity increases. So you should be able to apply this table, for example, hydrogen, carbon, nitrogen. As you see, the most electronegative atom here is fluorine. So when you see as a substituent, for example, if you have a compound to characterize, for example, this, if you just look at this, carbon has a substituent of hydrogen and also a chloride. Then if we were to draw a three-dimensional tetrahedral geometry, as I said, from now on, if you recognize this is an sp3 hybridized carbon, you should be able to draw a tetrahedral structure. That is hydrogen, that is another hydrogen coming out of the plane of the board into the plane of the board, and I will put chlorine on the plane of the board. You can put them anywhere else, it doesn't really matter. But to show you the dipole moment and the electronegativity, as you see here, between carbon and hydrogen, there is electronegative difference, a slight one, about 0.3. So carbon is more electronegative as compared to hydrogen. Therefore, the dipole moment should be drawn as like this. So exactly the same amount of dipole moment for carbon-hydrogen, the same amount. Here, when you just look at this, the carbon-chlorine is significant because 2.5, 3.2, it's about 0.7 difference. So it's very long dipole moment that is toward this chlorine. It's not toward this carbon now, it's toward this chlorine. It's pointing toward this chlorine. Obviously it makes sense because it has a more electronegative atom right there. So the dipole moment, there is a net dipole moment. So this has a net dipole moment, so it is a polar covalent molecule. It's polar and polar covalent. The bond is called polar covalent, that bond, the carbon-chlorine bond. Because there is no cancellation of the dipole moment. For example, this one is pointing that way. So you have to add them in a vector form or in a geometric form. But if you take CCl4, where you have carbon tetrachloride, central atom is carbon, chlorine, another chlorine out, another chlorine in, another chlorine on this plane of the board. So if you just look at this, there is a dipole moment, obviously. There is a dipole moment away. There is a dipole moment this way. There is a dipole moment all this. If you just look at this, all of the dipole moment cancels out and the dipole moment is zero dipole moment because they are pointing into opposite directions. If you just look at this, cancels out, and this is cancels out. So it's also dependent on the geometry of the molecule. Here it doesn't cancel out. Here it's adding this way, that way. For example, if you say this would cancel out, right? Actually, it wouldn't cancel out because it's pointing toward this carbon. So that will not be cancelled out. So there is a residual dipole moment in this case. So there is a dipole moment. It's not zero. And let's see another molecule, let's say carbon dioxide. Between carbon and oxygen, obviously there is a dipole moment about 0.9? I would say it's about 0.9, so it would be pointing toward this oxygen because oxygen is the most electronegative one. But there is another one like this. So carbon dioxide with no in a linear form, a linear molecule, no dipole moment. Hence, no dipole moment. How about water? If you remember, water has a bent geometry like this, lone pairs. So the dipole moment should point toward this oxygen. Obviously, oxygen is 3.4, but hydrogen is 2.2. That's almost 1.2 difference. So the dipole moment is this way, and the dipole vector this way. So both of the dipole moment will not cancel out. There will be a net dipole moment. So there is a dipole moment. That's why water is actually a polar molecule. It's a polar molecule. So based on a structure, the geometry, you can say a certain compound has dipole or a dipole moment. For example, another one, if you have a carbon-carbon double bond with chlorine that way, and here chlorine and one hydrogen here, the dipole moment between hydrogen and the carbon, there is a slight one, obviously, so it is a small one like this, and there is a small one like this, right? And also, the carbon-chlorine bond is highly polarized, a polar covalent bond, but this is this. So overall, if you just add up the vectors here, in terms of having the polar, this would cancel out. They are in opposite direction. And here it is from hydrogen to carbon. This is hydrogen to carbon. So there is a slight one, but in most cases this would cancel out. But if you compare it to this, where the chlorines are upside, both in and this side, dipole moment adds to that, dipole moment adds to that, so both are in the same direction, so there is a dipole moment. So there is a dipole moment. So if you compare this with this, this has more dipole moment, more polar, because of the shape, because of the geometry as well. So this would conclude the structure and bonding section of our lecture. Next time we'll continue the next session of the series.